All right, lesson 10, standard model and analyzing particle tracks. We're not going to worry too much about the standard model. We won't be testing this, but if you want to read through it, that's great. We're going to focus most of our time on analyzing the particle tracks. So feel free to read through this, but once again, I will not be testing on this material. So we're going to start here. So what is the purpose of these particle tracks? Well, particle tracks are ways that we can determine what other things are made out of, often by colliding particles together and seeing what as a result of these collisions. So what often we see is we can use something called a cloud chamber or a bubble chamber. And I'll see if I can find a video to post to guys, give you an example of what these may look like in real life. But in these cloud and bubble chambers, we're using the conservation of momentum, conservation of charge, lifespan, all the properties that we talked about before, and we're using these as detectors of these smaller particles. Once again, it says here the smaller particles are very short-lived and decay into other particles, but that's okay. So here are some particles that we've talked about in the past: protons, antiprotons, neutrons. Here's some other particles that are a little bit more beyond what we need to worry about. So lambdas, omegas, pions, kaons, and other particles that you'll see here. But the main thing we need to consider is the idea that what is its charge, what is its mass. We're not going to worry about this idea of spin. We're not going to worry too much about the quark content, but just know that the combination of ups and down quarks are often used to talk about these types of particles. All right, so let's take a look at this first question. So it says, these tracks show an antiproton, a charge of -1, colliding with a stationary proton. The resulting annihilation produces pions, both positive and negative. Solid line indicates the negative pions. What physics principle dictates that there must be equal number of positive and negative pions? So by having this through, we'll see the solid lines and the dotted lines, and there should be equal amounts of both. So it says, what physics principle dictates that there must be equal amounts? And that'd be the conservation of charge. So once again, if I had a positive proton followed by a negative proton and antiproton, in this case here we get a total of, it's neutral, so therefore everything after, so a combination of positive pions and negative pions must also be equal in order to conserve the conservation of charge. Okay, and then it says, what is the direction of the magnetic field? So this is going back to our hand rules and remembering the orientation of our hands. So once again, as a quick reminder, if you think about your hand, drawing my hand out real quick. Okay, if you remember, the thumb is the particle. The fingers are the field lines. And the palm, pointing directly perpendicular to both of those, once again, it's kind of hard to draw 3D, is the field direction. The force. Magnetic force. Okay, so magnetic force. So here we're going to take a look at this and see, well, if all of the negative particles are going this way, and all the positive particles are relatively going this way, so we're going to use our hands, remembering our right hand is positive, our left hand is negative. So if I position my fingers in such a way and see that all the particles going up, it's then spinning to the right. Spinning to the right, that means the fields must be going into the page. Okay, I'm going to say magnetic field into the page. All right, let's try the next question. Alpha particles, an electron, positron, and gamma ray create the following tracks. Identify the tracks. So in most cases, we're going to be talking about size. So the larger the particle, the larger the path would be. And speed is also a factor of this as well. So here we take a look at this and see that we have a very thick particle, most likely a larger particle. And then we have an electron, a positron, and a gamma ray. So it turns out that gamma rays, once again, first off, they're rays, they're not particles. And they're also neutral, so they will not actually deflect up nor down. So what we're going to see here is a particle are traveling to the right, and the magnetic field is into the page. So using your hand rules, we can take a look at this. I'm going to say that because of this, anything that is going up must be positive. So anything that's rotating in its upward direction will be positive. Anything going in this direction must be a negative. In this case, because we have an electron positron, we know that the relative size of these radiuses as this thing is rotating. So if you remember kind of back to Fm equals Fc, or QVB is equal to mv squared over r. So since both of these have the same radius, they must have the same relative charge, and they must also have the same relative mass. But maybe the charges is equal and opposite. So that means this one here, I'm going to say, well, this most likely is our positron, our positive electron, and this one here must be our negative electron. That being said, this being a thicker particle would most likely be our alpha particle here. Okay, once again, the path is bigger because the alpha particle is a lot bigger than that of the electron. Once again, you can look at your formula sheet to kind of see the relative sizes of these things. You can look at their masses and see how much more massive an alpha particle is compared to that of an electron. All right, let's take a look at this question here. A head-on collision between a proton and antiproton moving at the same speeds produces a pair of gamma photons. Determine the maximum frequency of each gamma. What conservation law suggests that the two photons produce rather than one? I think is what it's referring to here. And in this case, we're missing a little bit of information because it says moving at the same speed. It doesn't tell us what speed. The maximum frequency, remember, refers to E is equal to HF. So we're talking about energy conservation here. So maximum energy, I don't know if that's the right term. I would say probably minimum frequency. It might be a better term for this one because we don't know exactly what speed. But if a proton took all of its energy, and I'm going to say mass energy, in other words, mc squared for a proton, and then a antiproton, mc squared. All of this energy here, along with kinetic energy, would be used to produce these two photons. E is equal to HF, that's energy photon 1, and then also HF, photon number 2. So because two proton, antiproton, two particles, makes two photons after, and the reason for this is the law of conservation of momentum. You can't have a particle going in, two particles going in, having no momentum, total no momentum, and then you have a photon with momentum moving off in one direction. There must be equal amount of particles. So just kind of quick little visual of this. If I had two particles going equal in opposite directions, you can't simply have a single photon leaving with that energy, because technically before you had either zero momentum, therefore you must have zero momentum for the photons as well. There must always be pairs. So it has nothing to do with energy, has nothing to do with charge, but it has 100% to do with the momentum in this case here. So since two particles became two photons, we can simplify this and just say, hey, why don't we just think of this as mc squared equal HF, and we should be able to solve this through. So once again, this is not using the kinetic energy, when technically if these particles had speeds, they would also have kinetic energy that could account for some energy given to the photon as well. But we're going to simplify this in this case. So mc squared divided by h. As a reminder, we're using the mass of a proton. If you look at your formula sheet, we're going to say it's 1.67 times 10 to the negative 27 kilograms. Speed of light, 3 times 10 to the 8 meters per second, all that squared. And we're going to use a 6.63 times 10 to the 34 joules seconds to solve this one through. 1.67 times 10 to the negative 27 times 3 times 10 to the 8 squared divided by Planck's constant, 6.63 times 10. Oops. 6.63 times 10 to the negative 34 gives me an answer or frequency of 2.27 times 10 to the 23 hertz. Once again, that is from one photon or one proton to make one photon, and therefore the antiproton would also make another photon of equal frequency. All right, so that's it. Try these questions out. If you have any questions, please make sure you're asking. We are technically done all the material for Physics 30. Try them out. Once again, I posted something on Google Classroom to note that there will be no videos next week. It is just going to be review week. If you have any questions, please make sure you're asking. If there seems to be enough questions about the same material, maybe I'll post something. But your unit exam is not next week, but instead your unit exam will be the Wednesday, the last week of school. So June 24th, I posted on Google Classroom. But as a quick reminder, your exam is June 24th at 1 p.m. So study up for that. If you have any questions, please make sure you're asking Google Chat or through email. All right, guys, take care.